All right, so we're looking at 10.2. And 10.2 is another kind of intro into circles. So a lot of definitions, a lot of vocab stuff here, a lot of basics, naming stuff, which makes for a decently easy lesson here, as long as we know what they're asking us. Okay, so we're going to look at some vocab stuff here first. Looking at our circles. And we are talking specifically about arcs today. And an arc, as we know, is just part of the circle. An arc is part of the circle that has endpoints. So it's it's curved, it's part of that circle. First of all, they tell us the central angle. Central angle. We talk about central angles in regular polygons. A central angle of a circle is the same idea. Central angle is any angle that has the center as the vertex. That's considered a central angle. Unlike the regular polygons, they're not all congruent because we don't have specific points along the circle that we are going to, not like the polygons did. So we could have any number of different central angles there as long as the vertex is the center. Okay? If that central angle is less than 180, it is called a minor arc. So a minor arc is one that's less than 180, and a major arc is one that's bigger than 180. At 180, we would know is just the diameter. Right? If we take the diameter straight across, the two endpoints of my diameter would be 180 degrees, and that would be called a semicircle. Right? We've used that word before, I'm sure. But we've got minor arc is smaller than that, major arc is bigger than that. So we are going to be dealing with number of degrees that are bigger than 180 here, because we're dealing with arcs that are bigger than 180. They're bigger than that semicircle. Okay, that major arc goes further than that semicircle. Okay. So when we name these, when we name the arcs, they're named by their endpoints. Okay, but you'll notice the difference here. Pull it up a little bit. When I'm talking about the minor and the major arc here, the blue and the red, right? This one and then this one, they have the same endpoints. They both have the endpoints AB. So we can't just say arc AB. We got to find a way to determine which arc we're talking about, the minor or the major. So the way that we've come up with, if we simply say the two endpoints, just AB, that's going to be the minor arc. And you see we write it with that little arc symbol over it. Okay, make sure it's not a line, it's not line AB, it's arc AB with that little arc over it. If it just has two letters, that's a minor arc. Okay, if it has two letters, that's a minor arc, it's less than 180 degrees. If it's going to be either a semicircle or a major arc, so 180 degrees or bigger, we're going to name it with three letters. Okay, the two endpoints and then one other point that it's going through. So that's why you see the name ADB here. What that's telling us is we're going from A to B, but we're going through D to get there. So we're going A through D to get to B. That tells us it has to be this direction, which tells us that it's that major arc. That big difference there, and we have to know that difference when we're naming it. Okay, if it's just the two letters, it's a minor arc. If it's three letters, it's going to be the major arc or a semicircle. All right. Good deal. Questions on that? So you're either naming it with two or three letters there. So just make sure that we're naming it correctly. Even with the three letters, we still have that arc over it. Okay, we're still naming it correctly. I got a question. If they were both 180 degrees, would they both be major? No, we would call them the semicircles. So they wouldn't technically be major, but we would name them both with that third letter. So let's say that we had point E here. If we're talking about our semicircles, 180 degrees, we would have like EAB would be the top one, and then EDB would be the bottom. Okay, so we'd have two semicircles, both 180 degrees. We'd have to use that third letter though, so we know which side of the circle we're talking about. Good. Anything else right now? Okay. Good deal. Moving on. This is something that, at least the first part, I already told you because we used it in chapter 11. But the measure of a minor arc is the same thing as the central angle. Okay, we've talked about this before. But the measure of this arc, we did this when we were talking about arc length and sector area. Right? But this number of degrees is the same as this number of degrees. There's 360 degrees around my vertex. There's 360 degrees around the circle. So it matches up. If this is 50 degrees, then that arc is 50 degrees. And if I want to find the major arc, the measure of the major arc, then I can just have to subtract that number of degrees from 360. If I want the major arc here, ABB, and I know this central angle is 50, subtract that from 360, I know my major arc then is going to be 310. You just know they both have to add up. The minor and the major have to add up to 360. Okay. So then we're going to use that to be able to find some number of degrees. So if we look here, here's your circle. We know that one central angle is 110. I want you to find those three arc measures, please. Arc measures. Right, so if our central angle is 110, what is arc RS going to be? 110. How about arc RTS? What's that going to be? Oh, right.
So it's gonna be
250. Yep, because that's 360 minus 110. How about RST? RST, Luke?
180.
180. Right, we got a diameter. RST, 180 degrees. Good. Good deal. Okay, questions on that? All right. Other things that we can talk about here, this idea of adjacent arcs. Adjacent arcs are just two arcs that share an endpoint. They share an endpoint, they don't overlap, right? They share an endpoint, these are called adjacent arcs. And we have arc addition postulate. Just like way back in chapter 1, we had angle addition postulate and segment addition postulate. Same exact thing. We can take two arcs, we can add them together to equal a bigger arc. So we can take AB and BC, add it together. That's going to be the same as taking the measure of ABC. So as you can imagine, we are setting up some equations here, solving for X, that sort of thing. Take the two smaller arcs, add them together, equals the bigger arc. Should be pretty straightforward for that one. Let's practice that real quick. Okay, looking here, we're looking for GE, GEF, and GF. Why don't you go ahead and look at that, find those three arcs, please. All right, what is arc GE? Then we get test 120, add up that 40 and that 80, we get 120 from G to E. Okay, how about GEF? GEF, right?
190.
Not 190,
Oh, it's 170.
not 170.
Oh, what one? Oh, I did it wrong.
Somebody help me out. 230. 230.
I did it wrong.
Yep, GEF. GEF, right? So we got to add up the 40, the 80, and the 110. All of them. You get that 230. And then, so GF then, now GF is the minor arc here, Weston.
130.
130. We take that 230, which was the major arc, subtract it from 360. Good. All right, moving on. Other things, we got 3 theorems that we got to talk about here. So first of all, something that I wanted to point out here is that notice they are asking for the measure of the arc. In chapter 11, we talked about the length of the arc. So there's a difference when they're asking for measure versus length. Measure, the measure of the arc is a number of degrees. Okay, the length is going to be a number of inches or centimeters, something like that. So they ask for measure, they want number of degrees. So just keep that in mind. And they won't ask you for the length because according to this book, we don't know how to do that yet. So they're just going to ask you for the number of degrees. All right. So 3 theorems here that we got to talk about. First theorem, congruent circles theorem. And this is just telling us 2 circles are congruent if and only if they have the same radius. Really, that's the only measurement that we have when we talk about circles is the radius. So if they have the same radius, they are congruent. We could, or diameter, or something like that, but all of those are based off of radius, right? So all of that is also true, but our basic says if they have the same radius, then they're congruent. Okay. Remember, we name circles with a circle with a dot in it. That stands for circle, and then we use the center of it. So circle A is congruent to circle B when we have it listed. Okay, so we know that those are congruent. Okay. The next thing we talk about are congruent arcs. Congruent arcs are arcs that have the same measure. Well, there you go. But it's a little bit more than that. It can't just be the same measure, because what if I had a circle this big and a circle this big? And I'm looking at this arc and this arc, right? Yes, they have the same measure in terms of being 90 degrees, but are they congruent? Those arcs would not be the same length, right? So when we talk about congruent, we got to be careful. It says if and only if they have the same measure and they are arcs of the same circle or congruent circles. So we got to have either in the same circle. If they're in the same circle, then we're good, right? If these 2 angles are the same, then the 2 arcs are going to be the same. The 2 arcs are going to be congruent. Or if we have 2 circles where we know the circles are congruent, then we can apply that as well. So if I have 2 circles and I know this radius is 4 and this radius is 4, and then I talk about that 90 degrees, that's enough now to say that those are congruent. Because I've got congruent circles. I got circles that are the same size and the same number of degrees for this arc, then the arcs can be said to be congruent. So we just have to be careful on that we're not falling into this trap where they have the same number of degrees, but they're not the same size because one is obviously bigger than the other. Okay, so they're going to be congruent. They got to have the same number of degrees, but also they need to be of a circle with the same radius. If they're not of a circle with the same radius, then they're not actually congruent. Okay, just be careful of that, and we should be fine. And that's what our kind of what our next theorem gets into. In the same circle or in congruent circles, the arcs are congruent if and only if the central angles are. So it takes it a little bit further and says, all right, if we know the angles are congruent, then the arcs have to be congruent. If I know the arcs are congruent, then the angles have to be congruent. All right, it just goes back and forth. It is a biconditional. So we can use it either way. All right, but if we know these are congruent, then the angles are congruent. If the angles are congruent, then we know the arcs are congruent.
If two minor arcs are congruent, that means that the two major arcs have to be congruent.
Yeah, exactly. Yeah, because they're going to have the same number of degrees. So then the major arcs would have to have the same number of degrees as well. Yep. Anything else on that? Okay. So let's look at these three examples here. And they're asking us to say whether the red arcs are congruent or not. Are the red arcs congruent or not? Hopefully you can see which ones are red. We're talking CD and EF. We're talking RS and TU. And we're talking UV and YZ. Take a second to think about it. Okay, so for A, CD and EF, those arcs, are those arcs congruent? Yes, got a lot of head nods here. Yes, they are congruent because they have the same central angle, part of the same circle. They are congruent. Okay. How about for B, RS and TU? No, they are not. Somebody raise your hand and tell me, why are they not? How do I know that those are not actually congruent here? Toby?
Because their radiuses are the same.
Yeah, the radius is not the same length, right? This one's obviously smaller than this one. So just because they're both 90 degrees doesn't mean they are congruent because they're of different sizes. Good. C, yes or no? Are these good? Yeah? Yeah, they are good. Right? So now we've got different circles, but we know the radii are congruent. If the radii are congruent and our central angles are the same, then the arcs have to be the same. Good. Okay, questions on that? Okay. A lot of stuff in here, but it's a lot of little stuff. Right? It's not totally difficult. It's just we got to cover some stuff. The last theorem that we have, very difficult theorem. All circles are similar. All circles are similar. All right, we said similar figures in the past all have the same angle measures, same, and the side lengths were proportional. Well, we don't have angle measures now, so we don't have to worry about that. And in terms of side lengths being proportional, the only thing that we have are the radii. And the radii are always the same no matter where you have it in the circle. So they're always going to be proportional. Right? And whatever, if I want to find a scale factor, all I have to do is take those two radii and put one on top of the other. Because those are the only measurements that we have, really. So all circles are similar. We can find that scale factor just by putting our radii one on top of the other and simplify. And then the very last thing, they go through this whole proof of why they're similar. We're not going to touch that. Just the last thing is this idea of similar arcs. Similar arcs are just arcs that have the same measure. Okay, that's different than congruent arcs, right? So we got to know the difference between similar arcs and congruent arcs. Similar arcs are any two arcs that have the same measure. These two arcs I talked about here, these are similar arcs. They're both 90 degrees. Doesn't matter how big, how small the circle is. If they're 90 degrees, they are similar arcs. And then we talked about congruent arcs where it had to be the same size, right? So just know the difference between those, okay? Especially for like a vocab section, that would be important to know. The difference between similar arcs and congruent arcs. Okay. Good. Any questions about all of our arc stuff here?